In the previous chapters, we talked about finding the electric field due to a point charge or due to two charges that we also call a dipole, positive and negative charge, due to a ring. And in this video, now we will be calculating the magnetic field. The magnetic field is due to a current. So if you have a current carrying wire, a current carrying loop, or any structure, then we should be able to find out the magnetic field at a point. And this is done by using a Biot-Savart law. So let us consider we have a current carrying wire of any arbitrary form here. So this is not a straight wire, but any curved wire. And we are interested in finding out the magnetic field at point P. So what does the Biot-Savart law tells you? That the magnetic field at this point P, due to any elementary structure or a tiny length, due to this tiny length, here remember we are first calculating the magnetic field due to this tiny segment at point P, is given by this equation here. Mu naught divided by 4 pi I is the current passing through this tiny structure. dl vector is the direction of this tiny length. So the direction of this dl vector is in the direction of the current, and dl is the length of this structure here. R cross, this is a cross product, and r vector here, this is r hat or r unit vector. This is called a unit vector. And what does this unit vector tells you? That it tells you the direction of the point P with respect to this tiny element here. It does have a magnitude of 1. So the magnitude is just 1 of this r hat vector. Okay? And r is the distance between this elementary length and the point P. So once you know the magnetic field due to this tiny length, then we can find out the magnetic field due to this entire wire at this point P. And how do we do that? We can divide this entire wire into tiny segments or elementary length here. For example, this length here, and find out the magnetic field due to this all these tiny lengths. All right, and add them together. Or in other words, that we can find out the total magnetic field just by integrating this one due to this elementary magnetic field. So, and here the mu naught over 4 pi and d, these two are the constant, so I'm just taking all the constant outs, and I dl vectors, these are the variable quantity, so I'm keeping inside the integration. And here r is a variable, because if I choose this length, then this will be your r. If I choose this length, then this will be your r. So these are the variable quantities. All right. So this gives you the magnetic field, the total magnetic field due to this current carrying wire. Now let's talk about the constants here. The mu naught here is a constant, and the value of this constant is 4 pi times 10 to the negative 7 Newton per ampere square, or Tesla meter divided by ampere. And again, it is called the permeability constant, or mu naught in fact is called the permeability of free space. When I say free space, that means the air or vacuum. And what does this term means? What does this term means? The magnetic permeability is the property of a material. Okay, for example, when I say material, this wire here, this is just all the free space here. but this wire could be in fact placed in a wood or in water, or it can be placed in some liquid. It can be placed inside an iron or in plastic. So this wire, so that is called the medium. So the permeability, this magnetic permeability is the property of the material which tells us how strongly the material can support the development of magnetic field when placed in an external magnetic field. Or it also tells you that if you place this wire into a different medium, then how strongly the material can support the magnetic field inside the material. And I will talk about the magnetic permeability in a separate video here. So here I'm just introducing here, this is the material property. It is a constant quantity for any material that only tells you how strongly that material can support the development of the magnetic field. Okay, so this is, I mean, you also have studied, or I already have talked about the epsilon naught. That epsilon naught is the permittivity of free space. It's exactly the same thing here. When you talk about the electric field, we talk about the epsilon naught. When you talk about the magnetic field, then this is called permeability. So this one is related with the electric field, and this one is related with the magnetic field. So this one tells you how strongly the material can support the electric field, or this one tells you how strongly the material can support the magnetic field. So that's the material property. The one tells you about the electric field, the other talks you about the magnetic field. So far we talked about the magnetic field here. The magnitude of this one can be given by this way here. Let me write down the magnitude here. The B vector, the magnitude can be given by mu naught 4 pi I dl cross r vector, that's the magnitude, divided by r square. That's the magnitude. And this is a cross product. So the angle, so the cross product would be dl sine theta here. And theta is the angle between dl vector and r vector here. So this is the dl vector and that's the r vector. So theta is the angle between them. Okay. So if you already have taken the calculus class, you should be familiar with the cross product. So far we talked about the magnitude of the magnetic field. Now let us talk about the direction. How do we find out the direction? So here we're going to find out the direction by using right hand rule. What does the right hand rule tell you? If you hold this wire such that your thumb, this is your thumb, that points out in the direction of current, all right, then all these fingers here, the curl tells you the direction of the magnetic field. So when you hold a wire pointing your thumb in the direction of the current, then the direction in which your finger curls tells you the direction of magnetic field. In this case, these are the direction of the magnetic field. Okay, so at this point, now let's say at this point, the magnetic field will be encircling the circle, or it will be a circle here. So the magnetic field is looping around this wire here. All right, so this is a very powerful law to calculate the magnetic field. So this is it from this video. If you have any questions, write down your questions in the comment section below, and at the end, do not forget to like, share and subscribe the channel. Thank you very much.